Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Ahmad Nauman, and today in this lecture we will discuss about magnetic properties of advanced materials. This lecture is for BS Chemistry 6th semester students for the subject of Inorganic Material Chemistry. So first let's discuss that what are advanced materials, and after we know what are the advanced materials, then definitely we can go into the details of different kind of properties, including magnetic properties of the advanced materials. So the question is, what are the advanced materials? So by definition, advanced materials refer to all new materials or modification to existing materials in order to obtain superior performance in one or more characteristics that are critical for application under consideration. So what does it mean? एडवांस मटेरियल वो मटेरियल हैं कि जो किसी स्पेसिफिक एप्लीकेशन के लिए फॉर स्पेसिफिक एप्लीकेशन उनको डिज़ाइन किया जाता है टू गेट a better performance than already used materials. So those kind of materials are known as advanced materials. Or we can also say that existing materials, if they are used for some kind of application, for example, we have a material which is used for magnetic properties, but its properties are not up to the mark and we want to enhance the properties of that specific material. So we do some kind of modification in that material. That can be structural modification, or we can add some chemical compounds. We can maybe change the shape of the compound. So by those modification, we enhance the magnetic properties of that specific compound. So that material is also known as advanced material, in which their properties are enhanced. That can be any characteristic. For you can any materials whose properties, for example, magnetic properties are enhanced, electrical properties are enhanced, or whatever, and that is actually to be used for some specific application. So such materials are known as advanced materials. Example. So I know most of us, in maybe all of us who are listening to this, we are using smartphones. And we know that about Gorilla Glass, which is nowadays used in the cell phones. In fact, in the good phone, I think they are using Gorilla Glass 6 in the, if you talk about the Samsung's latest series of S20, so they are using Gorilla Glass, right? And before that, they were using simple glass materials, or which was prone to breakage. आपका फ़ोन हल्का सा गिरता था और ग्लास टूट जाता था, हल्का सा उसके ऊपर कोई प्रेशर पड़ता था और ग्लास टूट जाता था. सो व्हाट दे हैव डन इज they have improved that glass material, they have modified that materials so that it is more stress resistant and it is not easily breakable. So what we call that kind of material, we call it an advanced material. So Gorilla Glass, which is nowadays commonly used in the smartphone, is an advanced material, and is because it has the superior properties than the normal glass which is used for that purpose. Okay. So advanced materials may have improved properties, they should have improved properties over its replacement, and those properties can be different. For example, we are studying about magnetic properties, but in glass it is what we discuss about Gorilla Glass, so it has higher strength than the normal glass material, and in some cases there can be weight reduction, there can be strength, there can be higher conductivity or higher magnetism. So the overall, or in short, advanced materials are those materials in which we enhance a specific property of a specific material for its use in a certain specific application. Let's take another example of advanced materials. So we know that before that certain vehicles were made of the steel, and nowadays some advanced cars, they are using actually carbon fiber. Also, not only in cars, some other for example in bicycles, they are using carbon fiber. So it is an carbon fiber is an actually example of advanced material because it has enhanced or improved certain properties as compared to steel. For example, it is lighter in weight. So when compared with steel, carbon fibers are 75% lighter. And nowadays, if we talk about speed, because the normal vehicles can run at a very high speed, so for that they need to be lighter. So in this way, the carbon fiber is advantageous that it is almost 75% lighter than steel. But if we talk about its stiffness, it is almost 12 times that of steel. So it is not that although it is lighter, but it is very strong, the carbon fiber, and also it is more durable. So what happens that we are using carbon fiber instead of steel, so that it gives you lightweight, which enhances its speed, it gives you stiffness, and it gives you durability. So thus by using a carbon fiber, which is an advanced materials, we can enhance certain characteristics in normal used vehicles. Okay, so after introduction about advanced materials, let's discuss some other important terminologies, and then after that we will move ahead. So first, another term which is very commonly used nowadays, and we will be used a lot in this lecture and coming lectures, is nanomaterial. So what is a nanomaterial? So materials which have at least one dimension smaller than 100 nanometer is known as nanomaterial, and they can be much smaller in size, and they can be up to at atomic and molecular scale, that their size can be approximately 0.2 nanometer. But anything which is less than 100 nanometer in diameter is known as nanomaterial. Second is magnetic properties. So what are magnetic properties? A material which under the influence of its magnetic field can attract or repel other substances is known as a magnetic materials, and the properties of those materials of attraction and repulsion are known as magnetic properties. So the action of attracting or repelling a substance depends on the arrangement of electrons known as magnetic moment in the substance when brought under the influence of an external magnetic field. So जो mostly magnetic properties होती हैं materials की, that actually depends on the arrangement of electrons, and it also depends कि whether we have unpaired electrons or not, and also how they are arranged, and these things we will discuss in details in the coming slides. And just another definition, we will go through it and then we will move ahead, which is magnetic field. So magnetic field is actually an imaginary line of force around a magnet which enables other materials to get repelled or attracted towards it. It means that the area around a magnetic field where we can, our materials can feel और observe its effect. So किसी भी मैग्नेट के इर्द गिर्द और अराउंड वो एरिया जहाँ तक उसके इफेक्ट महसूस किए जा सकते हैं, उसको उस मटेरियल का मैग्नेटिक फील्ड कहा जाता है. So next we will study about magnetochemistry, which is the study of magnetic properties of materials. So as we discussed previously, so magnetic properties doesn't only mean whether a material will make a good or bad magnet, but it is also includes whether a material will be attracted or repelled by magnet. So it comes under the magnetic properties of a materials. And magnetism actually arise from moving charges that can be electrons, or that can be caused by the nucleus. So basically it arises from moving charges such as electric current in a coil of wire. And these magnetic properties also arise from the spin and orbital angular momentum of the electrons contained in a compound. So we will discuss it in next slides in detail. And we know that atoms are made of charged particles, which are protons and electrons, so which are moving constantly. Electrons are revolving around, so both protons and electron actually can create or can result in magnetic properties of a material. So magnetism or magnetic properties of materials can be induced or can be related with different properties in or different phenomena in a compound. So we will see those processes which create magnetic field in an atom, and broadly speaking we can say that magnetic properties, the intrinsic magnetic properties, are induced by the following three phenomena. First is the nuclear spin. So some nuclei, for example hydrogen atom, which have a net spin, can create a magnetic field. Besides nuclear spin, we know that electrons also spin around their axis, and because of that spin it can also result in the generation of magnetic field. And the third and the most important process which create magnetic field is the motion of electron around the nucleus. So that also results in the formation of magnetic field, which, and normally this contributes to the magnetic properties of a material.
Magnetization of material. Matter is made up of atoms, which are made up of electrons and a nucleus. The electrons revolve around the nucleus in a circular orbit, just as current carrying loop constitutes magnetic dipole moment. Electrons moving in these orbits also constitute magnetic dipole moment. Beside the orbital's motion, the electrons also have a spin motion along an axis similar to Earth's rotation. This spin also constitutes a magnetic moment which has a fixed magnitude of 9.285 into 10 to the power minus 24 joule per Tesla. The nucleus has a magnetic moment, but it is very negligible when compared to that of electrons. The resultant magnetic moment of an atom is the vector sum of all the magnetic moments in an atom. The resultant magnetic moment of an atom depends on the number of unpaired electrons in the atom. Some atom contains paired electrons in all their orbitals. For the sake of understanding, let us consider helium atom, which contains only one pair of electrons. The paired electrons have orbital motion and spin opposite to each other. Due to this, the magnetic moment of paired electrons have some magnitude but have opposite direction. The magnetic moments would then cancel each other out, and the resultant magnetic moment will be zero. Some elements have unpaired electrons in their orbitals. In such atoms, the magnetic moment of the unpaired electron is not cancelled due to the absence of the paired electron. Due to this, the resultant magnetic moment in the atom will not be equal to zero. The atom behaves like a tiny bar magnet. Every material consists more than one atom. Generally, the magnetic moments of these atoms are randomly oriented and the net dipole moment of the material is zero. However, when the material is placed in external magnetic field, the magnetic moments of these atoms tend to align themselves to the magnetic field and develop a net magnetic moment.
So each of these magnetic fields we observe in the previous animation and also on the previous slide, these can interact with one another and also with the external magnetic fields. However, these interactions can be of different type. They can be either strong, they can be very weak, or they can be negligible. So we will see that based on these kind of based on these interaction, they will actually decide whether we will have a strong magnetic material or weak magnetic materials or even non-magnetic material. Interaction between intrinsic spin of one electron and that of the intrinsic spin of another electron are actually the strongest one for very heavy elements such as actinides, and that phenomena is actually known as spin-spin coupling. So the interaction of the spin of one electron with the intrinsic spin of another electron, so this is when they interact with each other, so it is called spin-spin coupling. However, when an electron's intrinsic spin interacts with its orbital motion, then it is called spin-orbit coupling. And different macroscopic effects such as जब हम बात करते हैं मैग्नेटिक प्रॉपर्टीज की, स्पेशली जब हम मैग्नेट को देखते हैं तो हम कहते हैं कि जो मैग्नेट जो है वो मेटल को अट्रैक्ट करता है और इट इज़ अट्रैक्टेड टुवर्ड्स अ पीस ऑफ आयरन, या हमारे पास जो भी मेटल इस तरह के हैं जो मैग्नेटिक है. So that properties actually they are determined by the number of unpaired electrons. So the higher the number of electron, that actually the attraction of the or that magnetic property of that magnet or that material will be the higher. And not only the number of unpaired electron, but also the arrangement is also very important, and it also determines the magnetic properties and magnetic strength of a material. And there can be different possible cases when we study the magnetic properties or magnetic states of magnetic characteristics of materials, and we mostly call them magnetic states of matter. Another very important terminology which we should study when we are talking about magnetic properties of material is Weiss domains. So what are the Weiss domains? So every magnetic material is divided into magnetic domains called Weiss domains after a French physicist who predicted their existence theoretically in 1907. So first of all, the question is, what is a domain? A magnetic domain is a region within a magnetic material in which the magnetization is in a uniform direction. मैग्नेटिक डोमेन वो एरिया है, वो रीजन है किसी भी स्पेसिफिक मटेरियल के अंदर जिसके अंदर उसकी मैग्नेटाइजेशन जो होती है वो सेम यूनिफॉर्म डायरेक्शन में होती है, एक ही डायरेक्शन में होती है. विच मीन्स दैट इंडिविजुअल मैग्नेटिक जो मोमेंट्स हैं ऑफ द एटम, दे आर अलाइंड विद वन अनदर एंड दे पॉइंट इन द सेम डायरेक्शन. सो दिस इज व्हाट वी कॉल मैग्नेटिक डोमेन. And that is also we call it Weiss domain because it was first described by the French physicist Weiss in 1907. So when we expose magnetic material to an external magnetic field, what happens कि जो हमारे पास जो domains होते हैं जिनके अंदर जो magnetization होती है that is in same direction but they are in different patches. So in one part of a material they are although in the same direction the set of magnetization, but in another region they can be in also arranged but they are pointing in different direction. So when we apply a magnetic field, what happens that these boundaries of these domains they actually shift and they try to arrange themselves according to the applied magnetic field. So when we increase the magnetic field, more and more of those magnetic fields actually try to arrange themselves according to the applied magnetic field. This is the same when we see in the previous animation in which magnetic field is applied और उसकी जब strength increase होती है तो क्या होता है कि जो individual magnetization होती है, जो magnetic moment होता है वो shift करता है towards the direction of applied magnetic field. So same happens and these magnetic domains actually try to arrange themselves in the direction of the external magnetic field, and more domains shift towards the magnetic their direction towards the direction of magnetic field with increase in the strength of the magnetic field, and ultimately it happens that all of the domains are actually magnetized in the direction of magnetic field, and that material is then saturated, which means it attains the maximum magnetization, and thus we call it magnetically saturated. So जैसे हमने डिस्कस किया in the previous slide, so we can see here the top figure that we have different domains के different areas जहाँ पे जो magnetization है वो same direction में. For example, if we see in the top image on the left side, so we see that all the domains are in the upward direction, and if we see on the right side, we see that all are in the their direction is downwards. And also we can see there are 6 different domains in which the individual magnetizations are uniform, but they all domains actually differ from each other. So what happens कि जब हम जो नीचे वाली डायग्राम देखते हैं कि जब हमारे पास जो नॉर्मल जो मटेरियल होता है when we don't have any applied magnetic field, so these domains are there, so there are not uniformly arranged all the domains. So when we apply magnetic field, so what happens, as you can see in the second center image below, that some of the magnetic moments try to arrange themselves according to the magnetic field, and when we keep on increasing the strength of applied magnetic field, more and more domains arrange themselves according to the applied magnetic field. And if you see the last image on from the bottom, we see that all of the magnetic domains and are arranged according to the direction of the magnetic field. So this is actually known as the saturation of the magnetic material. So this is the representation of actually the Weiss domain which we discussed in the previous slide.
Now let's discuss about an important term called magnetization, also called as intensity of magnetization. When a magnetic material is subject to magnetizing force, the material becomes magnetized and develops a net magnetic moment that is not equal to 0. The intensity of magnetization helps us to measure to what extent the material is magnetized. It is defined as magnetic moment developed per unit volume of the material placed in the magnetizing field. Magnetization is equal to magnetic moment by volume. Magnetization is a vector quantity and its SI unit is ampere per meter. Before
So that was the introduction to magnetization and extent of magnetization and Weiss domains. And now we will discuss about the different types of magnetic substances. So when we place a material in magnetic field, so it give response in different ways. So based on the different responses of different materials to the applied magnetic field, we put them into different categories. So now we will study those types of magnetic substances. So broadly speaking, we can categorize magnetic material into diamagnetic substances, paramagnetic substances, ferromagnetic substances, antiferromagnetic substances, and ferrimagnetic substances. Now in coming slides we will go into details of diamagnetic substances and paramagnetic substances. We will discuss what are diamagnetic and paramagnetic substances and what is the underlying phenomena, and rest of the types, ferromagnetic, antiferromagnetic and ferrimagnetic substances, will be discussed in the next lecture. Among types of magnetic substances, we will first discuss about the diamagnetic substances. So in diamagnetic materials, for example, copper, silver and gold, atoms have no unpaired electrons. Thus, because if they have no unpaired electron, which means जो electron होंगे they will be in the form of pairs. So as we discussed previously, if we don't have unpaired electron, the pair of electron will have magnetic moments in opposite direction, and thus they will cancel out their magnetic moment. So thus in diamagnetic substances which have no unpaired electrons, the electrons will cancel out their magnetic moment and we will have zero net magnetic moment. And these diamagnetic substances are mostly weakly repelled when they are placed in a magnetic field. जब हम magnetic field apply करते हैं to a diamagnetic substance, then what happens कि the magnetic moment of electron, they actually align themselves in the opposite direction of the applied field. So normally we say that when we applied magnetic field, जो magnetic उनके domains होते हैं, they try to arrange in the direction of the applied magnetic field. But in case of the magnetic substances, the magnetic moments of electron, they align themselves in the opposite direction of the applied magnetic field. And also after we remove the magnetic field, then these magnetic moments, they do not these substances, they do not retain their magnetic moment and they come back to their original state.
Diamagnetism. In diamagnetic materials, the atoms contain fully filled paired electron orbitals. The vector sum of magnetic dipoles of all orbital electrons is zero. Hence, no permanent magnetism is found in such substances. At atomic level, the electrons revolve around the nucleus due to the centripetal force acting on it that is directed towards the center. Also, the velocity of the electron depends on the magnitude of centripetal force acting on it. When the diamagnetic material is placed in an external magnetic field, each of the orbital electrons experience a mechanical force called Lorentz Force. The direction of the Lorentz Force depends upon whether the electron is moving in clockwise direction or anti-clockwise direction. If the electron is moving in anti-clockwise direction, the Lorentz force acting on the electron will be in radially outward direction. Since these two forces are acting on the same line and in opposite direction, the effective centripetal force acting on the electron will decrease. Due to this, the velocity of the electron will also decrease. Hence, due to decrease in velocity, the magnetic dipole moment of the electron will decrease. On the other hand, in the case of electron which is moving in clockwise direction, the Lorentz force acting on the electron will be radially inward direction. Since these two forces are acting on the same line and in same direction, the effective centripetal force acting on the electron will increase. Due to this, the velocity of the electron will also increase. Due to increase in velocity, the magnetic dipole moment of the electron will increase. Similarly, all the electrons in various orbits experienced a change in magnetic moment. Some become short and some become long. Due to this, the atom develops a net magnetic moment in the direction opposite to that of the applied field.
The next type we will discuss is paramagnetic substances. So when a paramagnetic material is placed in a magnetic field, the magnetic moments of the atoms align themselves along the direction of applied magnetic field. So in contrast to the what we see in the diamagnetic substances, in paramagnetic substances जो when magnetic field apply करते हैं, the magnetic moments of the atom they actually align themselves as per the direction of the applied magnetic field. However, जब we remove the applied magnetic field, what happens कि these materials do not retain the magnetic moment and they come back to their original state. Thus in paramagnetic materials, जैसा कि हमारे पास एग्जांपल है ऑक्सीजन है, कॉपर 2 प्लस है, आयरन 3 प्लस है, मैग्नीशियम है, they mostly contain one or more unpaired electrons which actually cause their magnetic moment. And when we talk about the properties of magnetic substances, they are weakly attracted by the magnetic field because they have a very limited number of unpaired electrons. So let's see the diagram. इसमें हम देखते हैं कि जो हमारे normal जो diagram दी है, एक normal है, the other one is magnetic field applied and then a magnetic field removed. So if we look at the first diagram which is the showing the normal, so हम देखते हैं कि जो magnetic moment है they are not arranged, they are in the different directions. So जब हम magnetic field apply करते हैं, these all arrange themselves according to the magnetic field, so they are arranged in the same direction. So you can see from the direction of the arrow that the magnetic moments are arranged according to the direction of the applied magnetic field. However, we can see in the third diagram that when we remove the magnetic field, they come back to their original state. So this is the characteristics of the paramagnetic substances, that जब हम paramagnetic substances को magnetic field के अंदर रखते हैं, उनको अप्लाई करते हैं, तो जो उनके magnetic domains होते हैं, जो magnetic moments होते हैं, they arrange themselves according to the magnetic field. लेकिन जैसे ही हम applied magnetic field remove करेंगे, वो अपने original state पे वापस आ जाते हैं. So thus they are very weakly magnetic.
Paramagnetic materials. The atoms of paramagnetic materials have unpaired electrons in their orbits, due to which they have a permanent dipole moment. In the absence of external magnetic field, the magnetic moments of atoms are randomly oriented and the net dipole moment of such material is zero. When an external magnetic field is applied, the magnetic dipoles experiences a torque and tries to align in the direction of the applied magnetic field. At the same time, the thermal energy of the material opposes the alignment and tries to keep the dipoles in random orientation. Due to the opposing factors, only small number of dipoles align in the direction of magnetic field, and the magnetization intensity of that material will become non-zero. The magnetization of paramagnetic material depends on two major factors: temperature and external magnetic field. As the magnetic field increases, more number of dipoles can overcome the thermal energy and align with the magnetic field. The magnetization of the material increases. When temperature of the material is decreased, the thermal energy of the material decreases. Now, more number of dipoles can overcome this lower thermal energy and align with magnetic field. The magnetization increases. Again, if the temperature is increased, the thermal energy of the material increases. Now, some of the dipoles that already were aligned experience higher thermal energy and become randomly oriented. The magnetization decreases. Now, instead of external magnetic field B, it would be appropriate to use the term magnetic intensity H, which is the actual source of magnetic field. It is given by H is equal to B by mu. Therefore, we can say that the intensity of magnetization of paramagnetic materials is directly proportional to the applied magnetic intensity and inversely proportional to the absolute temperature. M is proportional to H by T. Removing the proportionality sign, the equation can be written as m is equal to C into h by t. Here, the constant of proportionality C is called Curie constant. Now let us discuss about an important term in magnetism called magnetic susceptibility. The magnetic susceptibility of material indicates how much a substance becomes magnetized when it is placed in an external magnetic field. It is denoted by this symbol, chi m. Magnetic susceptibility of material is defined as the ratio of intensity of magnetization m to the applied magnetizing force h. Chi m is equal to m by h. Since h and m have same units, the magnetic susceptibility is a unitless quantity. Now, if we consider this relation, m is proportional to h by t. This relation can be rewritten as m by h is proportional to 1 by t. Now let us replace m by h by magnetic susceptibility. Now, from this relation, we can say that magnetic susceptibility of a paramagnetic material is inversely proportional to absolute temperature. This relation is called Curie law in magnetism.
That's all for today's lecture. In this lecture, we briefly introduced advanced materials and nanomaterials. We also have some discussion about the basics of magnetization and extent of magnetization, and we also discuss in that regard wide domains and magnetic susceptibility. And then in the last we discussed types of magnetic substances, and today we study in detail about the diamagnetic substances and also the paramagnetic substances. And we have three more types of the magnetic substances which we will discuss in the next lecture. And also we have to study about the magnetic properties of advanced materials, so we will also cover that part also in the next lecture. So that was for today's lecture, and then I want to give you some homework. So before you attend your next lecture tomorrow, so before attending that lecture, I want you to study some basic terminologies. So first one is magnetic flux. So you should study about magnetic flux, that what is magnetic flux. It's not that difficult, it's very easy. It will take maybe only 5 minutes if you Google it, and then you will have understanding about what is magnetic flux. Similarly, we studied today about Lorentz Force, but I want you to Google it also and give it 5 or 10 minutes so that you can have a more better idea about what is Lorentz Force. And then there is another important terminology in magnetization, which we call it hysteresis, and it's really a important phenomena when we consider discuss ferromagnetic substances. So before next lecture, where we will discuss about ferromagnetic substances, so I expect from you guys to just spend 5 or 10 minutes and study about hysteresis. And the last one is Curie temperature. So please look for it, that what is Curie temperature. So I hope you guys will know the definition of Curie temperature, and also you will have some knowledge about these terminologies which I asked you to do at home. Okay, so that's all for today's lecture. Thank you so much for listening and your patience. In case you have any question related with this lecture, you're really free to ask. And thank you. Allah Hafiz.